Then I think we can go ahead and go on to the next presentation, which is by Andrew Ward, who is the principal statistician at the very well represented, I have to say, Social Research Centre in Melbourne, Australia. His interests and experience have focused on survey and official statistics, along with scale construction and validation. He's presenting on selecting candidate sets of calibration variables for sample surveys. Take it away.
Right, so thanks everyone for tuning in. I'm going to talk about some of our adventures in working with sample surveys and choosing weighting variables when there are plenty of characteristics available on the survey. So Dean and I have been working on this for a while at the Social Research Centre with tremendous help from our colleague Jack Barton. I'll just give a quick recap of weighting. So weighting is a very common survey done after, activity done after the survey, and it's aimed at enabling estimates for our population of interest. And the way we choose, well, which variables to use for weighting, there are numerous methods. A typical one or common is using geodemographics, so age, gender, location, something like that. Another approach, I'll call it the principled approach, if you like, and that's finding which characteristics are most associated with non-response to the survey and which are associated with the survey outcomes. So we'll call that a principled approach. There are other approaches as well. Maybe you're just going to be consistent with what you did last time. And in any event, the chosen weighting solution needs to produce survey estimates that have a low bias. That means our survey estimates align well with the population across our available characteristics. And they also have low variance. So here as a metric, we're going to use the Kish weighting frequency, or that's related to the effective sample size. So I just want to jump straight into what the crux of the problem is. Imagine you've got a survey, you've got lots of characteristics, and you try different combinations. You try your typical approach, you try your principled approach, and each time you do that, you calculate the mean absolute bias across all your characteristics. So that's the vertical axis, and lower is better. This is all percentage point differences. And for each weighting solution, you also calculate your Kish weighting efficiency. So that's on the horizontal axis, and for that one, higher is better. Now, ideally, you'd like a very low bias and very high efficiency, so that's in the bottom right corner. The way it pans out is really a bit like that. So, for instance, your typical solution is nice and efficient, but it doesn't necessarily reduce the bias across all your characteristics on average. The principled solution, that's the one where you choose variables correlated with outcomes and with response. So that's good. It reduces the bias, but the efficiency drops a fair bit. And in the solution space, there's a whole bunch of possibilities, and I've indicated some there where they've got low bias and much better efficiency than the principled solution. So we want to find those ones. So how can we find them? And I'm going to use a case study for Life in Australia. Winnie's just talked about Australia's online probability-based panel. And the good thing about Life in Australia is that we've got lots of characteristics that we've collected from our panellists. And the characteristics, we've aligned them with the Australian census and other sources, so that we've got really good high quality benchmarks for weighting. And with so many characteristics, how can we be sure that on average we're producing weights that have got good properties, so low bias and as high efficiency as possible? So we have from a pool of 27 characteristics, we just focused on solutions that have got 3 variables or 4 variables or 5 variables, all the way up to 8 variables. And once we enumerate all of those, eliminating the ones that aren't exactly compatible with each other, we end up with 500,000 combinations. So the low dimensional ones are very easy to do, but the high dimensional ones take a long time to do. So I've said there'd be 570 hours just on one of our PCs to run those. So that's not very plausible. So how can we deal with this? And we've come up with a number of approaches that we're trying to cover the solution space, but converge on what we think is the best result. So even though I've not mentioned it here, the principle, the typical solution would be one you try age, gender, location. Then we try a principled solution. So which of those variables are correlated with non-response and outcomes, and just choose those ones. But then, even though I said it's not plausible to do a complete enumeration, for our purposes here, we did do that. And we farmed them out across people's computers over a number of different days. And we could generate all 500,000 combinations. And through each combination, we calculated the average absolute bias and the weighting efficiency. And so from those more than 500,000, we could filter out the high bias ones, filter out the low efficiency ones, and we could come up with, after looking through the remainder, what we thought was the best solution overall. So that was a complete enumeration approach number 2. And then another approach was just take a random sample across the whole 500,000. Let's just use enough that we can run overnight. And then we did a more targeted one where we would run all the low dimensional ones, and then select the high dimensional, 4, 5, 6, 7, 8 variable ones that seem to be most likely to get a good result. So again, just a sampling approach. Then another approach we did was again start with a random sample across the whole data set, but then use a model. We used a gradient boost model to try and predict the bias and the efficiency for all the remaining cases. And then our final approach was we sort of went one dimension at a time, start with all the lower dimensional solutions, and then try and target the next dimension up, and then the next dimension up one at a time. So we've called that sequential enumeration, which is aiming at honing in on what we think is going to be the best solution. So with all these approaches, in the end you get a small or a large set of results, and we filter out the high bias and the low efficiency ones, and then look at what's left over and choose the best combination out of that. So here's where we ended up with all the different combinations we ran. So the principled approach is just one combination. You can run that straight away, but it didn't hit the target. The complete enumeration, well, that took a long time to run, and it's how we chose our overall best solution. Then we had the 2 sampling approaches, which sort of run overnight or in a day, and they also didn't get the target. The modelling approach, the gradient boost modelling, a bit of tuning time and everything, but it recovered the results, the ideal optimal solution. And then our sequential enumeration, we're calling it, doing a dimension at a time, was very quick, and it did recover the optimal solution. So I've got to say that all the results yielded a weighting solution you'd be happy enough with, the right variables and correlated with the things we expect. But none of the principled or the sampling approaches recovered, what we judged to be the optimal solution. The modelling approach, the gradient boost model on a subset of the data did, and the sequential enumeration, the one dimension at a time, they both did. The modelling, a bit of training and tuning time, which made it a bit longer to do, but still, within a day. And sequential enumeration was quick and easy to do, and we've tried it with some other ways of life in Australia and seem to work really well. So in our next steps are to keep applying our best approaches for other surveys. Particularly, we think it'll show a lot of promise for non-probability panels, where the bias can be a bit subtle or different from panel to panel. And we have some definitions and thresholds that we use for choosing cases, and we want to see how sensitive our final solution is to that. And perhaps we could improve the model tuning and training time for the gradient boost. So that's where we ended up to with that. So yeah, I just want to thank everyone for their attention, and I'll be happy to answer any questions.
Thank you very much. You came in like right spot on the amount of time. That was amazing. So let's see, we have a couple of questions. Measuring bias is somewhat subjective since it depends on which metric is used for measuring disparity and which benchmarks are used for external validity. What are your thoughts on making this critical measurement more robust?
Yeah, I guess we're starting off with a simple approach. So we thought that a nice two-dimensional average absolute bias coupled with the weighting efficiency was a good way to hone in on the results. And so we find that what we've done is get a good result that reduces the bias across all of our characteristics on average. But there's still some characteristics where the bias is still high, but the average washes that out a bit. So there's still some work to do about maybe prioritizing the variables in terms of what should get a higher weight in the bias calculation, and if there's still some real outliers that we need to worry about. So yeah, there's still plenty of work to do. So that's a really good question. Thanks.
And another question, how are you defining weighting efficiency here?
Oh, so that's a Kish weighting efficiency. So you can just look it up. It's the sum of the weights squared divided by the sum of the squared weights. I think I have that right. So yeah, just the Kish weighting efficiency, and it's related to the effective sample size. So again, just a simple metric that we can calculate really quickly, and that gives us a bit of a feel for how much variation there is in the weights.
Okay. Any other questions or follow-ups from the folks who had questions? Okay, good.
Lovely.
I thought it was very clear and very interesting.
Oh, lovely. Thanks so much, everyone. I really appreciate it.